distance, and everything gets tweaked in the quantum world. So one of the most important concepts of classical physics is the concept of a particle. Whenever you deal with the particles, your particle is a geometric point, something localized in space. In the quantum world, particles are not localized. Particles are spread. They are like waves. They are not in one point, but they're all everywhere. They can be all over the universe. So how much do particles spread? Well, it depends on a very important parameter that is called the de Broglie wavelength. Think of that de Broglie wavelength, that parameter lambda that I wrote on the board, as how much a particle spreads under a given condition. A particle is not a single point, but it spreads in space. So now, that condition involves the momentum. So there's a specific formula that says that depending on the linear momentum of the particle, you can calculate the spreading of the particle. Now, momentum is a cousin of kinetic energy. After all, you can write kinetic energy P squared over 2m, and kinetic energy of particles at a given temperature is proportional to the temperature. So therefore, the spreading of particles is related also to the temperature. Temperature is commensurate with the kinetic energy. From there you go to linear momentum, and then you go to the de Broglie formula. Now, it turns out that in order to have a large spreading of the particles, you need to lower the temperatures to those very low temperatures that are called absolute zero. Therefore, in order to see quantum effects, typically you need to keep the systems at very low temperatures. Now, what happens because of the quantum nature of the particles depends on many other parameters. But a very important other parameter is the average separation distance of the particle. So, therefore, that's the second row in there. So if the spreading of the particles is large relative to the separation between particles, then kind of the waves overlap, and therefore you see quantum behavior, pronounced quantum behavior. Now, if the spreading of the particle is very narrow and the separation distance is much larger than the spreading, then the particles are seen as localized, and basically you see a classical effect. So again, so this is a background story of what is quantum behavior, right? And so that you understand the terminology of the study, right? Lambda stands for wavelength, some length scale that has to do with the spreading of the particles. Now, we are surrounded by many particles. Right? The most important ones are those with the names of electrons, protons, neutrons, etc. But there are many other particles. It turns out that all the particles in the universe can be categorized as belonging to two groups. Right? So social particles, antisocial particles. Social particles are those that like each other, like to be friends, and like to stay together in a single state. Right? Single quantum states, they can stay all together. So they are social. So, however, there are many other particles that are antisocial. Right? So they have their state, they have their home, and they don't want anything else, any other particle of their nature to be there. So it turns out that the most important particles that I mentioned, electrons, protons, neutrons, are basically antisocial. So an electron, proton, and neutron is an antisocial particle. And these antisocial particles are called fermions. The social particles are called bosons. So what does it mean in the quantum world to be a fermion? It means that it is impossible to have two fermions in the same state. And that is the essence of the Pauli principle. The Pauli principle is one of the cornerstones of quantum physics. It says that if there is a quantum state, as it is determined by solving a very important equation of quantum physics called the Schrödinger equation, then there is only one and one particle, there is only one and one fermionic particle, a fermion, that can sit in that quantum state. So no other fermion is allowed in that quantum state. So that is the idea behind being antisocial. So one state, one particle. So these are the fermions. Pauli codified this principle many times ago, 1930s or so. This is the pioneering time of quantum physics, and it's a backbone of quantum physics and so many other phenomena. Kind of the structure of the atoms and the shells, etc., all come from the of the Pauli liquid. Now, in the classical world, particles may or may not interact with each other. Now, depending on the nature of the interaction between particles, you can classify the systems basically as gas, liquid, or solid. From the interactions, you basically say that, well, in a gas, the interactions are practically non-existent. Therefore, that's a gas. If the interactions are relatively weak, you say it's a liquid. And if the interactions are strong, then you say it's a solid. The same dictionary is used in quantum physics. Generally, when you say a quantum gas, we have in mind a system of particles that are not interacting, or a system of particles where the interactions between them are so weak that can be neglected. And therefore, this is the idea behind the theory of electron gases, etc. Now, if you want to put the interaction on top of them, because after all the electrons have charge and they interact by Coulomb forces, then well, you move on from the concept of gases to the concept of liquids. So liquids implies some interaction. If the interaction is strong, then you end up with a quantum solid. Quantum solid has a name in physics. It's called the Wigner solid, because it was predicted by Wigner again in 1930s. That was the golden age of quantum physics. And it was observed only very recently. It took like 70 years or so to finally have some evidence along the existence of Wigner solids. So now what Wigner said is that under quantum conditions and because of interactions, fermions, most notably he had in mind electrons, can solidify, can create a crystalline structure. Right? So now crystal, we mean crystalline structure. So what was the kind of motivation behind this work? In quantum physics, there is an orthodox belief that if fermions do not interact, they are always a gas. They cannot be a crystal. So until now, I believe that to be true again and again. So if there is no interaction, the state should be liquid or gas, whatever you want, but not solid, no crystal. So Wigner solids or Wigner crystals come only because of interaction. So that is the orthodox belief that has gone on for a very long time. So we all scientists who work in quantum physics who understand a portion of it, we believe that should be true. However, in 2017, 2 years ago, two interesting papers were published in two reputable journals. So one was published in Europhysics Letters by a European group, Guy et al., and another one was published in Nature. So these are all kind of highly respected papers. And these papers claim that in their treatment of non-interacting fermion systems, they saw crystalline structures. So they saw crystals, despite the fact that there was no interaction between the fermions. So therefore, they claim that there is a possibility that quantum behavior, under certain conditions when the fermions do not interact, might lead to a crystal state. Right? Crystal state. Right? So this goes against what I said, the orthodoxy. Right? What all scientists believe, what all quantum physicists believe. Right? So, again, when I heard that for the first time, I said probably they did something wrong with their calculations, and quite likely maybe they did something wrong. Right? But the idea is quite interesting. So, now, one of my old friends, who have been a student with me, that knows that when I was a PhD student, I worked with some theory that is called the statistical potential theory. Immediately encouraged me that, Orion, why did you sit down, write a theoretical model that would be easy for you because you have done those things as a student and you can do the calculations, the simulation. Right? So I said yes, and that was the motivation behind this work that started kind of during the summer. So I started the work to first debunk kind of the idea of Pauli crystals. As I said, so I belong to the orthodoxy that said if there is no interaction, we should not see crystals. Liquid or gas. So now, on the process of this work, kind of the results are depends how you see it. Neither no nor yes. I'm orthodox guy and believe there are no Pauli crystals, but something interesting came out of this work, and kind of these are the results that me and my collaborator reported and sent for publication to Annalen der Physik, and they are published now. The article is early view and maybe some hope is there. So again, perhaps a little bit too technical for some of you, but it has some nice pictures and figures. And so pretty much all the figures and pictures are from that paper. Again, so this is the background story. Now, so what is the claim here? What they say is, if you have fermions that do not interact, that should be a quantum gas. Exactly the same with the gas in classical world. The smoke will fill the whole universe. So in order to keep the smoke contained some way, you need a container. So therefore, for fermions, you need the container will be some sort of harmonic trap. So what is called a harmonic system or some 2D harmonic trap, a trapping potential. So otherwise the fermions will leave. So now, in order to treat the system so as cleanly as possible, well, you want to lower the dimensionality. So therefore the 2D world is a world where very interesting quantum effects happen. Therefore they deal with 2D systems of non-interacting systems, non-interacting fermions. Therefore, avoid the interactions, because the interactions lead to the dominant factor. You want to see only the quantum statistics, that Pauli principle that says that fermions are antisocial, therefore no two fermions can be in the same state. So you need to trap the particles, the fermions, and these fermions should be special. So they cannot be electrons, because whether we like it or not, the electrons have charge, and the repulsion between electrons will be a dominant factor. Because of repulsion, we might see crystalline structures. There is nothing out of this world about that. But they say that fermions should not interact, so therefore you don't want particles with charge. You don't want particles with any other form of interaction. That is important. So in this sense, you don't want to involve even what is responsible for magnetism, and in quantum physics that's a spin. So basically, you think of fermions with no magnetism, right? So spin polarized system. Under these conditions, at very low temperatures, so the lowest that they can go is 1 millikelvin, so that means very, very close to the absolute zero of the universe. So they say that they have seen some crystalline structures. So they published these results, as I said, in highly reputable journals. So those scientists are good scientists. They have a very robust output. I mean, so with very good papers, etc. So they look serious. Right? Sometimes there are hoaxes in science, so may not. So therefore, I took seriously what they have done, and just to check what might happen. So therefore, I was able to formulate a theory and model that is fairly straightforward. If you know the ideas behind the statistical interaction potential, and we got some results. I mean, so that I will show you shortly. Well, so here are those experiments that they report in these two papers. Right? So again, as I said, these are highly reputable journals. Now, pretty much what they do is statistical manipulation of system of fermions. So according to the rules of quantum physics, fermions are waves. They cannot be localized. It's a wave. It's everywhere in the pond, right? So, however, they say that if you take pictures of the system like millions of times and you gather all the data, then somehow after manipulating the data you will see that the fermions more or less have a preferred location in space where they stay. And therefore, after the data manipulation of this single shot experiments that they call it, so millions and millions of such data, they end up with this structure that I see. So that they see and they publish in their paper. Now, again, they say that if you have a system of 3 fermions in a 2D harmonic oscillator state, then so they can figure out that these 3 fermions form an equilateral triangle. So the center of the triangle is the center of the trap. confines them, and they arrange themselves into an equilateral triangle. It's a crystal, basically. Now, for 6 particles, they say that they see this structure that is a pentagon, 5 particles equally in a circle, and then one at the center of the trap. Now, again, as I said, so this particle fermions has to be trapped at very low temperatures, and therefore, typically they deal with those values of temperatures, the order of millikelvin, and the trapping energy commensurate with the temperature. So therefore, a very important parameter that you will see later on is the ratio of the two. Right? So, but again, so these are from their papers, right? So this is from their papers. Now, so they can do further analysis of larger systems. They can go up to 30 or 40 systems because it's very difficult to analyze all those millions and millions of data points. And so how they do it is, I mean, it's in their papers. It's very obscure. I don't work in that field. And well, so they say that they have a technique, they have a method to analyze the data, and from there they can extract kind of this crystalline structure. So when they say they come up with so these values for this type of crystal, what they see. But what is important is that the particles overall are not uniform now. So they are trying, so they are wandering around some size, right? It's a crystalline, so it's a kind of crystalline lattice. Now these numbers there, so when you go like 3, 6, etc., are the good quantum numbers if you know how to do the quantum mechanics of fermions in a 2D harmonic oscillator. Right? If you know a little bit of quantum physics, so if you read kind of the second section of my paper, kind of it explains that the good numbers are so 3, so 1 plus 2 plus 3 plus 4 plus 5, etc. So therefore, that's why you have so 3 and then 6, and then the other one should be 10, and then 15, etc. So these are called the field shells. Now, if you deviate from the field shells, then you are in trouble with quantum physics because the states become so the states become what we call degenerate, in the sense that there might be many different states that have exactly the same energy. Right? But that's where most of their calculations are done for closed shell structures. But these are the crystals that they notice in a harmonic trap. Now, so this is kind of the simplest example of going away from that magic number of closed shells. Right? So it was 3 and 6, so therefore this will be with 5 fermions. So this is a very strange structure. I would expect it some symmetrical patterns, but they say that so if you have 5 fermions in a harmonic trap under confinement, well, you get something like a trapezoid. Again, so it's difficult to deal with open shells, but again, so these are the results reported. Well, now the simplest thing that I could do, based on my knowledge of how to formulate a model that might relate to the quantum treatment that they do, is to deal with the simplest system. And indeed, so if you have to deal with 3 or 6 fermions, I could deal with them analytically up to a certain point. You can do calculation, pencil and paper up to a certain point, and then sooner or later you have to use the computer to get something, in order to get something numerical. But again, so that was the easy part. So now they reported in their data how this equilateral triangle or this pentagon looks like. So they said that, well, under those conditions that the experiments were done, let's say, so the ratio of KBT, that would be temperature with the energy of confinement, H bar omega was 1, alpha 1 were the experiments that they did. And for such experiments and the internal structure of the fermions, the so-called harmonic oscillator length can be calculated and tells you that this structure is this equilateral triangle, kind of with the side length such and such, to give the number. So this pentagon is such and such pentagon with a particle in the center, 5 in the circle, with a radius such and such. So these values, so they were reported in their paper. So therefore, so the first check would be that, well, can we build a model that captures the quantum physics and leads to some analytic result, right? Something that we can compare with those experiments. And that is the idea behind the so-called statistical interaction model or statistical potential. So the idea is simple. It originates again from the 30s. That's the golden age of physics. So there's a work by Uhlenbeck and Gropper. Now I knew that, so these works have been forgotten, but I moved them many times ago. So now, what they do is to say that there is a recipe how you can map a quantum system of fermions that do not interact with a classical system of particles that interact with some effective potential that mimics the quantum repulsion of fermion particles. So again, we said that fermions are antisocial, therefore it is like effectively they don't like each other and they repel. So bosons are social and they effectively like each other and attract. So therefore, if you follow the recipe, you end up with the recipe is quite general. You end up with a semi-classical, effective way of dealing with the Pauli's principle. In essence, the Pauli principle says that if a fermion is here, the second one is coming to his home, he's repelled. So therefore, there is some effective repulsion that can be treated. And therefore, you see these two lines. Again, the theory is a little bit technical, but again, you end up with the red line that is always positive and grows. Again, so it means that the two fermions are coming close to each other. A positive effective potential means strong repulsion. Fermion 1 doesn't like fermion 2. But the blue line is negative. That means so boson 1 likes boson 2. So for bosons are social, they like each other, they effectively attract in the classical sense, but fermions effectively repel in the classical sense. So now, is this realistic or not? Well, it's a classical representation, but this is the best that you can do. Because you have to deal with a quantum system that otherwise, so you don't know how to deal it. Because, again, so there are so many issues with even with the problem of quantum measurement. Measuring a quantum system implies that if you find a result, it doesn't mean that that was the state of the system when you measure it. The state of the system was anything else, it was a superposition of many states. Even the act of measurement kind of rules what was the state of the system that you are measuring. So therefore, this is the best that we can do. And at least we have a tool to mimic those experiments with a model that can lead to pure quantitative results. Yeah, so this is something perfectly doable. Well, and as I said, so calculations can be done analytically for small systems. 3 and 6 particles, you can do the calculations analytically up to a certain point. Now remember what I found for 3 systems is an equilateral triangle. Now this is from my work in the paper. Under the same condition, parameter alpha is something that has to do with the temperature that was considered. Well, we found this value that is more or less analytical. That represents kind of the distance of each of the 3 particles from the center of the trap. Now, so if you compare with the result of this study, this is fairly close. So the difference is about 3%. That is pretty good for a classical model. Very good for a classical model. Now, for 6 particles, they see the structure of one in the center and the pentagon. We could do the calculations analytically even for such a structure. Right? So up to a certain point. Right? Sooner or later, you reach a certain point and you have to use numerical tools to get the values. Right? So, but it's a fairly doable analytical calculation. Now, for the same conditions of the experiment, well, so we found the pentagon in agreement with what they say,
And with the geometry, that is in very good agreement with what they report in their paper, right? So again, so if you do the math of those numbers, what I obtain and what do they obtain, so the disagreement is about 3%, but I would be very worried if we are in a good agreement, right? So in fact, I want to debunk their calculations. I hope that so my hope was to be in total disagreement with them, to say that something is wrong with their papers. Because again, as I said, I repeat it again, so the orthodox belief is that Pauli crystals should not exist. Well, now, this looks like, well, there is something interesting there, but again, it's a story of two halves, right? So now, when we tried the calculations for, again, even a simpler system of 5 particles, when they saw those trapezoids, there was no way that our model generated the trapezoids that they saw, right? So if you go backwards, you see that these are very strange structure, right? If you put our 5 particles on a harmonic trap, we ended up with the most stable structure that was those 5 particles on a pentagon. So not like that. So again, so they say that it's like a trapezoid. So in our case, we got this particle here, in disagreement with that. So now, again, so that is, there is agreement here for these small systems, but the best to do is to go to as large system as you can. Now, finding the minimum energy configuration of a large system of interacting particles, even though they are classical, our model is classical, they are interacting with this statistical interaction potential, is a nightmare from the computational point of view. It's a very difficult simulation to be done. It has to be done by computer. Right? So that is where my friend Joseph Butler kind of is good. He does simulation, right? But it's very painful, right? So because you have many particles, and when the particles move, any motion of the particles kind of may decrease or increase the energy, and you want to find what is the lowest energy possible in the system. Many times the system gets trapped in what are called local minima. You want the global minimum of energy, but it's trapped in a local minima. Therefore, it's very hard to find the minimum energy of system. Now, one of the most famous problems in physics is the so-called Thomson problem that says, can you find what is the minimum energy configuration of, let's say, n electrons that are forced to be on the surface of the sphere? Well, so this problem has not been solved analytically even for systems consisting of 6 particles. So it has been done for 5 particles. So the lowest energy of a system of 5 electrons on a sphere is 3 of them form an equilateral triangle along the equator. One is the northern pole, the other one is the southern pole. So this paper has been published only 4 years ago, and it is 84 pages of calculations. To find that it cannot be done. Anything should be done numerically. It's very hard. But again, so we tried the best that we could to see what our model generates for larger structures. So again, so these are 3 fermions. This is 6 fermions. Kind of the largest one. The largest one that we want to study is the one with 15 fermions. So now, experiments can be done at any temperature, right? So therefore, the simulations should mimic the temperature. So if the temperature is 1 millikelvin, you use alpha 1, right? So, but if the temperature is slightly different, our parameter can be slightly different. So, and well, look at kind of the different structures that we obtained from our simulations with 15 particles. So again, red and green correspond to a structure with 1 at the center, 4 in the first shell, and 10 in the other shell. However, the blue one means that whatever was in the center now has moved away. Therefore, kind of these numbers 1, 4, 10 represent the shells. So 1 means 1 in the center, 4 in the second shell, 10 in the third shell. But the structure 510 means that there is nothing at the center, there is 5. The blue means there is 5 in the shell, and the 10 there is in the larger shell. So therefore, the temperature kind of affects the stability of the system. So now 1410 corresponds to the right temperature of this. So the structure 1410 is the structure of alpha equal to 1 of their experiment. So therefore, we are in disagreement with them. So what they see is 1 at the center. So what they see is 1 at the center, and so something like this, 159. So again, there is disagreement. So might be small disagreement, but it is disagreement, right? So again, now one might argue that in their experiments somehow they could not eliminate the interaction. Everything might go wrong. Right? So therefore, there is some remnant interaction, and therefore remnant interactions should lead to sort of crystalline structures along the lines of Wigner crystals that I described right at the beginning. Right? So now, Wigner crystals stabilized by interaction have been very well studied. So again, if you put n charges, these point charges like electrons in a harmonic trap, then you know exactly what are the most stable crystals that arise there. It is the interaction that leads to the crystalline state. That's not a problem. So, in their model, there's no interaction whatsoever. Now, when you look at the literature, there's a nice work by Peters and Beranov. They give the Wigner crystals for any sort of system, right? So for 15 particles, so they say that the structure is 510, so it is not 159. So therefore, it's kind of interesting. So the Pauli crystal that they say they have seen is not a Wigner crystal. Right? So now, it resembles what we see, but our structure is highly dependent on the temperature. Therefore, we are there in that realm that we don't know what to say. We don't know what to say. Well, so the largest simulation that we could do, and that is it's very painful to do the simulation. They go on for days and days and days, and so there is a specific method called Monte Carlo annealing method that is highly technical, but these are done by my collaborator. So this is the largest structure that you could find. So now, I searched those 3 papers from 2017 to see if they've done anything for 30 particles, but well, that's why there's an empty space there. Apparently they haven't done it. So they could not manage to do this calculation, so this statement for 30 particles. So I don't know what to say. I mean, but this is the structure that we see. So now, the only thing that we can say for sure is that, well, so our structure that has 4 shells, and the inner shell has 4 particles, so it is not a Wigner solid, because from the literature we know that the Wigner solid should have 5 particles in the first concentric shell. Nevertheless, if you believe the literature, so these groups that I mentioned, so they say that the Pauli crystal has exactly the same structure of a Coulomb crystal. It looks a little bit suspicious along the lines that perhaps some remnant, very weak interaction in their treatment leads to something that resembles a Wigner crystal. But since after all, the Wigner crystal has been studied for decades, and it is not something out of this world. Now, to cut it short, these results indicate that something interesting to the idea. Do they debunk the idea? No. Do they support the idea? No. After all, you can always say that our classical or semi-classical treatment cannot ever capture the nature of the quantum correlations that are enshrined on the Pauli's principle. And that is a very fair argument. quantum correlations are very difficult to estimate because in principle they're all what we call many-body correlations. Here we come to the technical. Our treatment can capture these correlations only at the two-body level. Therefore, we just say that fragment 1 interacts with fragment 2. That looks surprising to you, but we have 3 body interactions, 4 body interactions, etc. So all of these are enshrined in the nature of the quantum correlations. In fact, so there is no recipe. So there is no recipe of how to effectively study a quantum system. Because even the act of measurement per se disturbs the quantum state that you are trying to measure. So therefore, that is a realm that everybody can speculate. And these authors of these 2 papers kind of know the subject. Basically, they have put their hands before everything, and they say that, well, so everybody might disagree with us, but we know that these are quantum correlations, therefore they cannot be taken care by effective methods, and so on and so forth. Now, to conclude, now, so the most important statement in my paper is kind of that line in the abstract. We thought many days how to craft the conclusions. We didn't want to say they do not exist, so I would have been inclined to say that, well, so Pauli crystals are something that we don't believe that they should exist in the realm of quantum physics, but again, so this is how we phrase everything, because you have to kind of give a message to the audience, to the community. Therefore, in a very politically correct way, so what we said that it is not clear whether Pauli crystalline structures do really exist in a quantum system, or whether they are artifacts of the methods used to analyze them. Wink, wink. So maybe they did something wrong. That's what it is. So that is a polite way to say that their treatment might have something that it's hard for anybody to figure it out, but it's maybe some artifact of the method that they use. So that would be kind of, if you read under the lines, right? So that's a key message. That's a key message of this paper. And hopefully, I know that there are some others that are following on their paper, and we'll see what happens. I mean, everything might go wrong in their single-shot measurements, their techniques that they use, etc. Even a minor thing that goes wrong kind of will deduct our make those results very suspicious. Now, from the theoretical point of view, I repeat that there is absolutely no shred of evidence of Pauli crystals. Again, so orthodox quantum physics says that they should not exist, right? So they should not exist. But again, so this is the nature of science. I mean, so you have to be open-minded. You hear what the other says, right? So you try to prove or disprove that, and then you make a kind of honest statement about whether you think what has been done is valid or solid or not. So therefore, we are in that realm. Now, again, so I always point out that the treatment that we did in this work is classical and therefore kind of has its weak points, but there's nothing better that can be done. Short of repeating again their studies and see if you end up with the same conclusions. Right? So, and others can do that because you need to be highly knowledgeable in what they do. For me and my collaborators and others, it's very difficult to understand what really might have gone one way or another way in their study. In short, so whether the Pauli crystals do exist or not, it's something that will be seen in the future. Personally, I belong to that orthodox school, but they should not exist. So, well, my calculation neither support nor deny them. There is something interesting to the idea, but what might be? So the future is something that will be seen. With all that said, I have also to acknowledge my good friend for many years. We write papers together, etc. Joseph Butler. He's from Spain, from the beautiful island of Mallorca, the University of Balearic Islands. He did the simulation, we did all the theory, all the paper. And of course, I mean, so you need common practice for us when you go to various symposiums or conferences. So gratefully acknowledge our sponsors who provide the means of carrying out this work. And sometimes they support me, sometimes they support the students, and as Dr. Storr mentioned it. So I always try to hire students to work with me, and so I let them work on those projects. And pretty much I tailor the projects to the level of the student. I ask the student to do the simulation, it will be impossible. But you need to tailor it to the student. Okay, with that said, so thank you very much for your attendance.